अभी तो नहीं किया ना, यहाँ से आपको दिख जाएंगे ना ये सब। This one mute.
Ma'am, good morning, ma'am.
Good morning. Can you hear me? Students, if you can hear me,
Yes,
you
ma'am.
can type.
Clearly, ma'am.
All
Yes.
right, great.
Good morning.
Good
Good afternoon.
morning. It's nice to see you all here. Okay, so notice one thing. I'm here to answer your questions. I'm here to look at your doubts and see where I can clarify the concepts better, which will help you prepare for the exam. Now, if you have any questions, please type in the chat. And I will take the questions from the chat one by one. And as I'm explaining each question, if you want further clarification, you can raise your hand. So if you look at the bottom of the screen, there is a raise hand icon which looks like a palm. So if you click on the palm, I will know that which student has a question regarding what I'm asking. So don't unmute yourself unless I invite you to. So once you raise your hand, I may invite you to unmute yourself and ask what's going on. Meanwhile, please start writing your questions in the chat. And my suggestion would be, instead of asking very specific questions like how do I solve this question, ask about general problems that you have. That, hey, I know how to find the Jacobian, but then I don't know how to draw the phase portrait. Okay, so we have a question from SK. Thank you, SK. Can you explain different types of bifurcations again, particularly if there is any arithmetic test to test for the type of bifurcation? Very good. So yes, I'll be very happy to explain to you the different kinds of bifurcation. Let me share the screen first. I hope you're able to see my screen. So we are going to start with understanding what bifurcations look like. So I hope this is a good revision for everybody in the class. So remember, okay, this is not how I wanted to write it. Let me erase and rewrite this. It's a new software that I'm using, so it's taking me a while to get used to it. Hold on. Okay, so the thing about bifurcation is when we change a parameter, the number of fixed points or the quality of fixed points should change. So when we are looking for bifurcation, we are looking for two things: number of fixed points. I'm abbreviating fixed point as FP, and the second thing is quality of fixed point. So here is a quick recap of the kinds of bifurcation. The first is saddle node bifurcation. It's one of the easiest kind of bifurcation to figure out. What saddle node bifurcation means is that it is the bifurcation when suddenly the number of fixed points go up. The quality of fixed points doesn't change. So, or either they go up or they go down. So this is the bifurcation where new fixed points appear or disappear. The other kind of bifurcation that we are dealing with is, okay, hold on, I'm seeing that some of the stuff that I'm writing is not coming on the screen. The other kind of bifurcation that we deal with is transcritical bifurcation. Transcritical bifurcation is when the number of fixed points remains the same, but the quality of fixed points changes after a critical point. So, for example, let's say we had let's say this is x-axis. So here we have fixed points on y-axis and we have a parameter r on x-axis. So let's say when r is positive, we have two fixed points, and one fixed point follows a line and it's a stable fixed point. And as r approaches 0, this particular fixed point also approaches 0. So this is fixed point number 1. So let's say the other fixed point is equal to 4, always equal to 4, plus 4. So let's say the 4 is somewhere here, and it's an unstable fixed point. So we have a situation like this. So we have two fixed points. Here is a critical point. Why is this a critical point? Because the two fixed points are coalescing with each other, they are coinciding with each other. And after this fixed point, if this unstable fixed point becomes a stable fixed point, and the stable fixed point, which was the line passing through the center, becomes an unstable fixed point. So let me change the color so I can show you unstable. It becomes an unstable fixed point, then this is transcritical bifurcation. Please note one thing, students, that there are only two things that will tell me what kind of bifurcation is happening: number of fixed points and quality of fixed point. So far we have revised two kinds of fixed points, saddle node and transcritical. Saddle node is when number of fixed points changes. You have new fixed points arise or new fixed points disappear, old fixed points disappear after a critical point. In transcritical bifurcation, no new fixed points happen, no fixed points disappear, but the quality of fixed points changes after the critical point. For example, here after the critical point, what was a stable fixed point becomes an unstable fixed point. What was an unstable fixed point becomes a stable fixed point. So this is a transcritical bifurcation. We have another kind of bifurcation, which is pitchfork. Now pitchfork classically looks like a pitchfork bifurcation, that's why it is called pitchfork bifurcation. But I like to think of pitchfork bifurcation as a summation of both, the first two kinds of bifurcation, which is, yes, new fixed points appear or disappear when we are dealing with around the critical point, but also the quality of fixed points reverses. So in pitchfork bifurcation, there will be at least one. There will be, let me change the color to make this little more clear. So there will be at least one fixed point who will always be present, but it will change its quality of fixed point. So for example, let's say here it was an unstable fixed point. So I'm showing it by dashed green line. This is a fixed point whose value is 0. So it will always remain the fixed point, but as the critical point 0 is crossed, it will become a stable fixed point. This is a quality of transcritical. But also as the critical threshold of 0 is crossed, it will also have two new fixed points appear, which are also unstable, let's say. So now we have one scenario where we can say a set of new fixed points have appeared. So number one criteria is met, and the existing fixed point has reversed its state, has reversed its stability. So the second criteria is also met. When both criteria are met, it's pitchfork bifurcation. Now to answer the second part of your question, is there any arithmetic way to find this out? My advice would be, don't rely on arithmetic ways. It's going to be very tricky. There are ways to figure it out, but it's much more trickier than what I have taught you. Okay, for example, delta is less than 0, simple test. So now here is the thing, SK, I think this is a very good question about delta equal to 0. Arithmetic, what you are sharing with me about is, it depends upon the way in which the model is written. Now if my model is written as a quadratic equation, yes, I can talk about the what its determinant would be, what in my, we can say what tau square minus 4 delta would be, whether the roots are imaginary, whether the roots are real, whether my fixed points are going to appear or disappear. But my saddle node bifurcation will not always look like a quadratic equation. Yeah, remember that. Okay, so delta less than 0 or more than 0 is also a condition which will be only valid when your model looks a certain way, which is not always going to be the case. So the easiest way for you is to actually use the geometric approach. SK has another follow-up question: what is subcritical versus supercritical business? Okay, so subcritical versus supercritical business becomes very, very relevant when we are looking at subcritical slowing down or supercritical speeding up around the critical point, and these are only relevant in case of pitchfork bifurcation. They are not very important at this stage, but since I covered them in the class, I'll give you a brief refresher. Briefly, subcritical and supercritical, you can understand them this way, that whether the pitchfork, the shape of the pitchfork is like what we say trishul in Hindi. So pitchfork is used for tuning, it can be a tuning fork. So whether the pitchfork appears, okay, I need to share the screen again. So whether the pitchfork, which in this case appears to the left side, right? So it is subcritical, or it appears, if it appears to the right side, then it will be supercritical. Now, where it is important, why it is important to look at subcritical and supercritical is that when we approach 0, or when we approach the critical point, what is happening to the rate at which my variable is changing? What's happening to the rate at which my fixed points are changing? Now, if I have new unstable fixed points emerging at the critical point, which is the diagram that I drew. So let me share the screen again. So in this particular case, you can see that at the critical point, to the left side of it, new fixed points are arising, and the two new fixed points that are arising are unstable fixed points, right? So here in the neighborhood, what is happening in the neighborhood, that is actually much more important than deciding whether I'm going to deal with a supercritical slowing down or a supercritical speeding up of my system, of my fixed points. Now, the way I talked about it in the class is, in the online class, is whether the whether the pitchfork is happening to the left or to the right. Here it's happening to the left, so this is subcritical. If it was happening to the right, for example, so let's say these are my fixed points and this is my parameter. So if my situation looked something like this, let me change. Okay, I see what is happening here. Let me change the color to show the unstable fixed point. So here the pitchfork is happening to the right side, so this will be supercritical. Okay, let's see other questions. Folks, please share your questions in the chat. If you want a general primer over how to draw the phase portraits, how to understand what this whole Jacobian business is, how to deal with nonlinear equations, 2D nonlinear equations. If you want a short, yes, Vinita, the class will be recorded, is being recorded and will be shared. But yes, if you have any general doubt, you can feel free to ask that too. Since there are no more questions regarding any particular topic for now, I will just continue a little bit more about bifurcations. So the way I encourage you to find out what kind of bifurcation is happening in a particular system is to first, for any value of the parameters, now you can have one parameter or two parameter, for any given value of parameter, try to find out the number of fixed points and the quality of fixed points. So what you're doing is you're drawing a phase portrait and you're trying to see, okay, for a given value of parameters, This is how the face portrait looks like. And then start varying those parameters and go from minus infinity 0 to plus infinity for all the parameters that you are varying. Now as you vary them, you will see that some fixed points may appear, some old fixed points may disappear. You may see that some fixed points may change their stability after a critical point. So that will give you information on what kind of bifurcation is happening. And then the last step in bifurcation analysis is to actually draw the bifurcation plot, which is, I know, very tricky even for my students that I teach at IIT Roorkee in person, and we practice it a lot in the class, how to draw the bifurcation plot. And the way to draw bifurcation plot, I will again share the screen and show you. So let's say I have drawn my face portraits for varying values of the parameters. Then draw a simple 2D graph. On x-axis, write the parameter that you are varying. So let's say r is a parameter that you are varying, and on y-axis you are drawing fixed points. This is very important. You are drawing fixed points on the y-axis. So what you're trying to see is that for a given, and then now here, let's say this was your initial value of r when you started your face portrait. For a given value of r, how many fixed points do you have? Plot them here. Plot them perpendicularly to this point. So let's say you took r greater than 0, not very small value, decent size value, and let's say you had one fixed point here, another fixed point here, and another fixed point here. As you increase the value, then once you have done this, increase the value of r to plus infinity and see how the value changes, how these fixed points change. Maybe these two fixed points are stable fixed points who converge as you increase the value of r. Maybe this is an unstable fixed point that eventually reaches 0 as r tends to infinity. So this is how you will get an idea of what your bifurcation diagram looks like as r tends to infinity. Now make r come to the 0. Notice what happens when r comes to 0. So what you're doing is you're redrawing the face portraits as r is coming closer to 0 or even becoming 0. And then you're going to repeat the whole process. You're going to draw the fixed points for different values of r, and then you're going to join them together. Now here is the thing. The question that you should wonder about is, there are infinite points between 0 and my initial value of r. Am I going to draw infinite fixed points? No, you're not going to draw infinite fixed points. That's pretty obvious. You're going to take certain values, and I don't even take values now. My students here don't take. We just try to understand what's happening when the parameter is equal to 0. Okay, when parameter is equal to 0, then one fixed point is minus infinity. Let's say the other fixed point is 0, and then the other fixed point is a very large number. So then we know that, okay, this fixed point can be joined here, this probably approaches minus infinity, and then this becomes a very large number. So we do not need to know the exact values for all the points. We just need to know for important points, and then you can join and make your bifurcation diagram. Okay, let's go back to your questions. Okay, I have some very general questions about the exam here. Can we have detailed solutions of all the assignments, madam? Okay, I'll ask my TA to share with you detailed solutions for all assignments. I think this will be very helpful for you folks. Ma'am, please explain finding fixed point using trigonometric function. Satya, this is a great question. I'm going to do it now. This is the question I'm going to take up, but let me look at some shorter questions that I can answer right away before I take your question up. So, Debayan, coming back to you, I will ask my TA to share detailed solutions for all assignments. So let me make a note of it before I forget. Alrighty, so this will be done, yeah? Okay, coming to Satya's question, please explain finding fixed points using trigonometric functions. Okay, let me change my paper and then we'll start. So, when you say using trigonometric functions, I'm assuming, correct me if I'm wrong, Satya, and you can use chats. By trigonometric functions, you mean when my model has trigonometric functions in them, yeah? At least that's the assumption I'm making. So I'm going to take an example and I'm going to help you answer it. I'm going to take 2 examples and I hope it's helpful for everybody. And in case you already know how to do this, folks, still pay attention. You never know what extra you're going to learn, what extra clarification you're going to get. Okay. So, Satya, let's say we are starting with this question. Dx by dt is equal to half. Well, okay, this is an easy question, okay? I'll start with an easy question and then I'll give you a not so easy question. Half minus sine x, okay? Now, how do I find out the fixed points in this particular case? Now, sine x is a periodic function. Half is a straight line. My principle when solving these kind of models is, can I make it easy for me? Can I make my life easier instead of finding out for all the values of x when sine x will be equal to half, which is also pretty easy. I took an easy example, remember? Is to split my model into 2 functions that are getting subtracted. So there's a subtraction sign here, which makes my life very easy. This is function 1, let's say, function 1, and this is function 2. Function 1 minus function 2, that is what is happening here, yeah? So, if function 1 is greater than function 2, then dx by dt will be positive. Please note here, if we have a situation where function 1 and function 2 are getting subtracted. If function 1 is bigger than function 2, then dx by dt will be positive. If function 1 is less than function 2, then dx by dt will be negative. If function 1 is equal to function 2, then dx by dt will be equal to 0, and we will be dealing with a situation where we have fixed points. Yeah, there is some lag between what I'm writing and what's showing up on the screen. I'll try to do my best. Okay, so in order to make understand where the fixed points are, when I try to draw the phase portrait, so here I'll plot x, here I'll plot dx by dt. First draw the function 1, whatever the function 1 is. Here the function 1 is very straightforward, it is a constant. So function 1 is a constant, it's a straight line. So this is function 1. And this is half. The second is draw the function 2. Remember, we are drawing function 2. We are not drawing minus sine x, we are drawing sine x, which is function 2. Function 1 was half, function 2 is sine x. So sine x at 0 will be 0. And then at a certain value, we know theta is equal to 90 will be. So we are going to be dealing with something like this kind of scenario. Now wherever the intersection is happening, that is the point where f1 is equal to f2. Wherever these 2 functions are intersecting, these are my fixed points. Yeah, this was an easy example. Let's take another example. Oh, by the way, let's also figure out the stability of these 2 fixed points. So there are infinite fixed points for this system, you can imagine, and you can make this graph bigger and see how they look like and what they're.
How is judge half stable and half unstable and half stable? No? Avid with the recipe.
Please write your questions in the chat. Do not unmute yourself for those who just joined. Let me restate the rules. Do not unmute yourself to ask a question. If you have a question when I'm explaining something, like right now, raise your hand. There is a raise hand option at the bottom of your screen. Click on it. Yeah. And if you have any new question, please type it in the chat. I will go through all the questions. And if we don't have enough time to go through all the questions today, I'll try to extend the time. And if that's not possible, we'll reschedule another live session next week. Okay? I'm here to help you, but please do not interrupt. Your question is, by the way, very welcome. I'm going to talk about half stable, half unstable too, but please type it in the chat. Okay, coming back to the question that I was looking at, I want to show you how to figure out the stability. And as promised, I'll also look at a slightly trickier situation when we are dealing with trigonometric functions. Okay, so here, how do we figure out the stability of these two fixed points? Now, to figure out stability of any two fixed points, what you need to understand is what is the sign of dx by dt in the neighborhood of the fixed points. At the fixed point, dx by dt is definitely equal to 0. That is given. That is how we define fixed points. But what is happening around the fixed point is going to tell me what the stability of the fixed point is. So let's start with this fixed point, the first fixed point that I have drawn here. To the left of this fixed point, so if I go to the left side of this fixed point, in the neighborhood of this fixed point, the line, the constant, the line is above the curve, right? Which means function 1, this is function 1, remember. Function 1 is above function 2. When in Cartesian geometry, function 1 is above function 2, it means that the function 1 is bigger than function 2. Function 1 is bigger than function 2. So when this is bigger than sine x, their subtraction will be positive. So here I know that dx by dt is positive to the left side of the fixed point. Now let's look at what happens in the immediate right side of the fixed point. To the right side of the fixed point, function 1 is below function 2. Which means function 1, this term, is smaller than function 2. Because it is below, it is smaller. And remember, both can be negative, both can be positive, doesn't matter. Function 1 is below function 2. Which means I'm subtracting a bigger term from a smaller term. Which means dx by dt is going to be negative. So to the right side, dx by dt is less than 0. Yeah, so let's look at these two information that I have. On left side of the fixed point, dx by dt is positive. What does it mean? Think about it. What does it mean when dx by dt is positive? When dx by dt is positive, it means that your x is going to increase. You might be very close to negative infinity, you might be very close to plus infinity, you might be anywhere in your Cartesian plane, but your dx by dt is positive, means your x is going to increase. So remember, x is on x-axis here. So x is going to increase, means the flow is going to be towards right side. Let me change the color to draw this part. The flow is going to be towards right side. Clear? Because dx by dt is positive. To the right of the fixed point, dx by dt is negative. It's less than 0. Which means x is going to reduce. Think about it. What happens when dx by dt is less than 0? X reduces. X may be positive, x may be 0, x may be negative, doesn't matter. Dx by dt is negative, x is going to reduce. So x is on x-axis, it's going to reduce. It means the movement is going to be towards negative infinity, towards left side. So if I look at only the first fixed point that I have drawn here, both the arrows are pointing towards the fixed point. When this happens, we are dealing with a stable fixed point. The way to show stable fixed point in the exam is to draw a circle and then color it completely like I have done here. Clear? This is your stable fixed point. Now think about it. Why is it called stable fixed point? Because if I move slightly to the left side, if I try to leave this fixed point and move slightly to the left, what will happen? Dx by dt will start increasing, dx by dt is positive, x will start increasing, and I'll come back. The flow will push me back to the fixed point. Now if I start going to the right side of the fixed point to run away, for whatever reason, to move away from the fixed point, what will happen? Dx by dt is negative, x will start reducing, and I'll be pushed back by the flow back to the fixed point. So this is a stable fixed point. Now let's look at the second fixed point that we have drawn here, which is here. Let's figure out its stability. So we notice that to the left of the fixed point, the line is below the curve, f1 is below f2, f1 is less than f2, so dx by dt is going to be negative. To the right side of this fixed point, f1 is above f2. Let me change the color again to not confuse anybody. Yeah, so f1 is above f2, f1 is bigger than f2, so dx by dt is going to be positive to the right side. By now you know what this means. When dx by dt is positive, x is going to increase, so your flow, I'm going to change the color again, your flow is going to be towards right side because x is increasing. Now if you look at this fixed point, to the left side of the fixed point the flow is towards left, to the right side the flow is to the right. So both arrows are pointing away from the fixed point. So this is an unstable fixed point. Let's see what happens when I start from the unstable fixed point. I will always stay at the unstable fixed point. But if I introduce some perturbation and I force this object to move slightly to the left, what will happen? As it moves away from the fixed point slightly to the left, dx by dt is negative, it will keep on reducing. It will move further and further away from the fixed point. Similarly, if I force it to move slightly to the right, what will happen? Dx by dt is positive, it will keep on increasing till the plus infinity or till the next fixed point. So you see, this is an unstable fixed point. As long as things are at unstable fixed point, that's fine. The moment there is a perturbation, they'll either move to the left or to the right. Now, since one of you asked me the question about half stable, half unstable, I don't like jumping questions, but I think I can include that question here. So let's say I'm dealing with a situation where my face portrait looks something like this. Yeah, so this is dx by dt and this is my function, only one function. Okay, no subtraction of functions like we did in the previous case. Let's figure out the stabilities of these fixed points. So how many fixed points do we have? How do you know how many fixed points you have? You're going to find out, to find fixed points, you need to find out all the scenarios where dx by dt is equal to 0. So, okay, this is hard. Where dx by dt is equal to 0. So dx by dt is equal to 0 here, it's equal to 0 here, and it's equal to 0 here. So we have 3 fixed points. Let's figure out the stability of these fixed points. To the left of this fixed point, the curve dx by dt is positive. Remember, the curve that we are drawing is dx by dt. This is not the same question, this is a different question. Okay, this is a different question that we are dealing with. Please don't confuse yourself. What I have drawn is dx by dt versus x. This is a face portrait. So here dx by dt is positive, so the flow will be to the right because x will increase. Between these two fixed points, the flow will be to the left because dx by dt is negative, less than 0. Which means if x is somewhere here, dx by dt is negative, so x will reduce and move towards left side. Similarly, between these two fixed points, dx by dt is positive, which means that between these two fixed points, x will increase, x will move towards right side. Now between the last fixed point and plus infinity, x is also going to, dx by dt is positive, which means x is going to increase. So we have this scenario. Now how do we decide the stability of the fixed point? Let's start from the first fixed point. Arrows are pointing towards the fixed point, so this is stable. Arrows are moving away from the fixed point, unstable. Now this is an interesting case. The left arrow is moving towards it, so it seems that yes, this is a stable fixed point, but the right arrow is moving away from it, so I'm not sure if it is stable or not. In this case, we are dealing with a scenario where this is half stable, it's half stable to the left side, and it is half unstable to the right. So let me redraw this in a different color. Just this fixed point in a different color. This is a half stable fixed point. So I have colored half of the circle green, the other half I have left. The reason why I have colored the left half of the circle is because it is stable on the left half, not on the right half. Okay, I promise that I will take a look at a slightly more tricky version of this, but I'm thinking that let me see how many questions there are. If there aren't many questions, then I will take a slightly more tricky question and solve it. But let me see what other questions we have. Question paper pattern. You're right. Ma'am, have never taken a pen paper mode of NPTEL. Could you give a preview of the type of questions? You know what? All the questions will be numericals that you'll have to answer. A couple of them, well, I think only 1 or 2 marks, maybe maximum 5 marks questions are questions which require you to write down the answer in words. Most of them just require you to draw diagrams, bifurcation diagrams. If you know how to draw face portraits, if you know how to draw bifurcation diagram, if you know how to interpret the model, you're good. But I think I should provide you a sample of some questions to give you an idea of how the questions will look like. That would be helpful. But I will solve it now. I will definitely solve a question which will be slightly more trickier version of the question that I showed you how to solve, which was half minus sine x, to help you understand the kind of questions that may come in the exam. Okay. Ma'am, in the whole course, what all must be remembered? You said we need not remember specific models. Do we need to remember Lotka-Volterra, predator, prey, exponential? Okay. So, yes, you do not need to remember Lotka-Volterra. No. In fact, Lotka-Volterra family of models is just one family of many models. There are so many models that there's no way to even cover them in a single class. And I do not want you to remember the models. I want you to remember how to interpret the models. I want you to remember how to draw their face portraits. If there's a bifurcation going on, how to do that. How to figure out the kind of bifurcation. How to figure out the bifurcation plots. How to interpret the constants. How to non-dimensionalize the model. I want you to remember those principles. I don't want you to memorize. Okay, the other question SK is asking, what happens when we are exactly on the parabolic curve of tau delta? Good question. So, what happens when tau square minus 4 delta is exactly equal to 0? So, SK, look at the diagram I shared in the class. And in that diagram, there is a small arrow which writes down what happens. So, take a look at it, and if you still have a question, come back and ask again, and I'll tell you. Okay, Satya, I have already answered the question about half stable and half unstable. Imperfect and perfect transcritical bifurcation. Supercritical, subcritical, half bifurcation. How to check for stable manifold in a system. These are a lot of good questions, SK. Ma'am, for first and second order systems, please provide us with some shortcut tests to figure out the types of bifurcation. Okay. let's start with your first question. Imperfect and perfect transcritical bifurcation. So imperfect and perfect bifurcation can happen with any kind of bifurcation, not just transcritical. I mean, even imperfect pitchfork bifurcations exist. A lot of outbreak models rely on it. And even imperfect Hoff bifurcation exists. It's not limited to transcritical. Please be clear about that. Now, imperfection arises when your system is no longer symmetric. When your system is symmetric, the bifurcation plot looks very tidy. For example, if you remember the pitchfork diagram that I drew earlier, it's very tidy. The new fixed points appear exactly where the critical point is, exactly when the switch happens between stability of the ever existing fixed point. But when imperfections arises, that the plots no longer look very simple. That's all what imperfection means. Imperfection in this regard is not a new mathematical stuff that's happening. It just means that your model is no longer symmetric around x-axis or around y-axis. I'll give you an example. So let's say so let's go back and look at this particular scenario here. So you see here, okay, hold on. So you see here, I was explaining to you what pitchfork bifurcation looks like, and this is a very neat diagram of a pitchfork bifurcation. Yeah, because the new fixed points are appearing here, and it's exactly around 0 that this is also the existent fixed point is switching its stability. It's all neat and tidy. It looks very nice. Now if I look at this particular diagram, if here I change something, let's change one small little feature here. So let's say okay, I'm really gonna struggle with this. Yeah, it's hard to redraw using this surface, but let's say that to the right of this particular critical value of R, the third fixed point was a stable fixed point, and the moment the new fixed points appeared, it was unstable. So what's happening here is that there is a switch in stability, and also at the same time new fixed points are appearing. So this is an example of pitchfork bifurcation, but doesn't look neat and tidy as the pitchfork bifurcation in the green looks like, because the switch in stability is happening somewhere here, but the new fixed points are arising here, even though they are all happening. Okay, this is slightly to the left, but let's just assume that this is also happening here, are all happening at the same critical value of R critical. So this is an example where I have introduced imperfection. There is nothing otherwise special about any kind of imperfection. Same is true with subcritical, with imperfection if I introduce it to Hoff bifurcation. Subcritical and supercritical Hoff bifurcation. Okay, is that what you meant when you asked me about subcritical and supercritical earlier? Okay, so subcritical and supercritical Hoff. I don't remember how in depth I went when I was teaching you about subcritical and supercritical Hoff bifurcation. Let me check this really quickly, because if I didn't go very in depth, I will not ask you. I will not explain to you in depth either. Because I don't think I covered Hoff bifurcation in much detail in the class. Okay, so I don't think I explained to you in much details, so I just checked my syllabus. So I'm going to explain to you very simply what subcritical and supercritical Hoff are and what's the difference between them. Again, sharing my screen. Very simply, all you need to know of the difference between subcritical and supercritical Hoff bifurcation is what is happening. So there has to be, let's take first the example of a supercritical Hoff. I need to screen up. Here we are. Change the color is good. Supercritical Hoff. So supercritical Hoff. So let's say this is a stable limit cycle. Yeah? And there is an unstable fixed point here inside the stable limit cycle. Then we are dealing with the supercritical Hoff. Now, subcritical Hoff reverses the situation. This is all you need to know for this course. Hoff is a very important class of bifurcations that are extremely important in ecological systems and medical systems, but they are a study of their own. So I did not cover them in detail because we already have a very packed course. But this is all you need to know for now. And if the limit cycle is unstable, so we are reversing them, unstable, and you have a stable fixed point inside, then we are dealing with the subcritical Hoff. The movement, the flow lines in both will look very different. As you can imagine, the movement in both will look very different. So stable is an attractor. Yeah? So your movement may look like this. This is a repeller, so your movement will look different. Yeah? That's all you need to know. Okay. Let's take other questions. How do you check for a stable manifold in a system? I think stable manifold example I gave when we were talking about one of the Lotka-Volterra models. So, and in that Lotka-Volterra model, what had happened was for coexistence, we had a fine line, a very thin line where coexistence was a possibility. And then to the north and south of that thin line, we were dealing with extinction of either of the species. Is that when I talked about stable manifold? I think that is when I talked about stable manifold. Okay. So how to check for stable manifold in a system? For stable manifold, when you will draw the phase portrait, you will get clarity about what is happening. Also, I don't ever ask people to find out stable manifold in this course. It's a sort of introductory course for modeling. I don't expect people to really know. But once you draw the phase portrait, you will get clear about where the stable manifold is, if it is there. For first and second order system, please provide us with some shortcut to find out types of bifurcation. There are no shortcuts. I can give you practice questions. I totally intend to do that. And I will, if time permits, I will solve a question or two with you here. If not this week, then next week, and we'll go over how to find out different kinds of bifurcation. Please practice numericals. That's the only way you can understand how, most of your questions will be answered. How to find fixed points, how to find out their stability, what is half stable, half unstable. How do I check for bifurcation? Please give a shortcut. There is no shortcut. Even my students here at IIT Roorkee who sit with me 3 times a week trying to solve, they also sweat a lot when I ask them to draw a bifurcation plot, because they're like, oh, too much. And with 2D systems, it's going to be easy because I never give difficult questions with 2D. It's already very hard. So if you know how to do it in 1D, you'll be able to do it in 2D. But 1D is also very tricky. Bifurcation diagram is a very difficult, very lengthy, very time-consuming thing to do. It requires the brain too. So please practice. I'll give you practice questions. SK has another question. Do fixed points appear or disappear in pairs? Are there only odd number of fixed points in case of saddle node cases? Very interesting question. The saddle node cases that I have talked about so far, the new fixed points appear or disappear because we are dealing with a quadratic equation. Now in quadratic equation, the roots will either become imaginary and the fixed points will disappear, or they'll become real and the fixed points will appear in pairs. But you're right, depending on the system, they don't have to appear or disappear in pairs. We can just have a new fixed point appear, a singular fixed point, or an odd number of fixed points appear. Will questions in exam also? No coding. When I teach the same course here, which I'm doing this semester, there is a MATLAB exam, 3-hour exam, but not here. Since it will be a pen paper mode of exam, will there be step marking too? There will always be step marking, always, in this course. Any derivation type of question will arise for models? Yes, I love asking derivation questions, where I'll give you a very rudimentary model, I'll ask you to non-dimensionalize it. So make sure you practice how to non-dimensionalize systems, and then I'll ask you to draw the phase portrait. So I'll give you practice questions, so make sure you practice how to draw phase portraits. If there's a bifurcation going on, I'll ask you to do that too. Figure the bifurcation out, draw the bifurcation diagram, and then I'll ask you to interpret. Sometimes I ask to interpret the constants. So for example, what does A mean here? For example, there's a constant in the model called A. Then you have to figure out, is A the growth rate, is A the death rate, what's happening, what does A represent? Or I'll ask you to interpret the phase portrait. So maybe one of the fixed points stands for extinction of a species, the other stands for outbreak of the species. So yeah. So yes, I'll ask you how to interpret the results or the model itself. These are the kind of questions. Okay. Ma'am, any derivation? Ma'am, question was in the assignment regarding half bifurcation. Okay, SK, I'll have to ask my TA to see what questions are there in the assignment. I've forgotten about that. I will get back to you about this though. I don't have my TA with me. He's not well today. So as soon as he recovers, I'll get the questions from him, and I will not only ask him to share the solutions, because that has been requested earlier for all the assignments in detail, but I'll also ask him to bring up the half bifurcation related question, and then I'll answer it. Thanks for letting me know that. Let me write that down before I forget though. This is important. Half bifurcations are some of my favorite, most important. Okay. Ma'am, will you please explain multi-phase diffusion with practical examples? Okay, so I think I use practical examples in the lectures too. So multi-phase diffusion is when the diffusion is happening through multiple phases. So maybe the diffusion is happening through solid, liquid and gas. All three of the phases the diffusion is happening. Now let's think of some examples where this might be happening. So let's say we are, okay, this is a far-fetched, it's not a very practical from Indian perspective, but let's say we are sitting on we are looking at an underwater volcano. right? And gases are slowly diffusing out. They're under pressure, but the ocean also has a lot of weight, so they're balancing each other out. But the gases are slowly diffusing out of the rocks. So the diffusion is happening through the rocks, and then the volcanic gases are entering the water, and then they're slowly diffusing through the water. So now the diffusion is happening through the liquid, and then maybe they'll escape into the air, and then the diffusion will happen in the air. So this is an example of multi-phase diffusion. Let's look at a more closer to our real life example. So let's say we have a chimney and we are releasing certain pollutants from the chimney, and there is a particular pollutant X that I want to get rid of. So what I can do is I can have a scrubbing system in place to get rid of the pollutant X, and the gases, the flume may first pass through a liquid or a liquid shower. So that will be the first level of stripping, and some diffusion might happen through the liquid too, and then it might go through a solid porous adsorbent where diffusion might happen through the diffusion might happen inside the solid surface or through the air. So this is another example where diffusion is happening through different phases. When we talk about multi-phase, do not get confused about having multi in your term. Remember that for solids, for liquids, and for gases, there are certain constants that you need to be very clear about. For example, there will be an equilibrium constant. Within equilibrium constant will tell me what the concentration should be, and the equilibrium constant can be liquid to gas, gas to solid, gas liquid and solid. So there can be interface equilibrium constants, there can be within phase, intraphase equilibrium constants, there can be partition coefficients which are interface equilibrium constants. That's all you need to know. And remember, when we are talking about diffusion, we are talking about under motion. It's a temperature dependent process. It is moving always towards lower concentration. So if another example, let me think of more examples of multi-phase diffusion that are very relevant from environmental science perspective. My mind keeps on going towards the gases releasing at the bottom of the lake or bottom of the ocean. But for example, aerating aeration tank in a activated sludge-based process-based STP. So now I'm aerating, so of course we are forming bubbles, there is advection, but part of aeration is also carried on by diffusion. Now the diffusion is going through a mixed phase media, because in an aeration tank we have biomass, which is suspended solids, and then we have water. So now the diffusion is happening through both the suspended solids and through the water. So this is another example of diffusion happening at the same time through two different phases. It's a multi-phase diffusion. Okay, let's see. SK has, okay, star and degenerate node. I talked about star nodes and degenerate nodes before SK. So let me help you here. Star node is when all the flow lines come to the fixed point as straight lines. So if you remember one way in our keyboards, if you look at your keyboard, if you are using a keyboard, above 8, number 8, there is an asterisk sign. Asterisk stands for star. So what is that star? All the lines coming to the center of the star are straight lines. When this is the case in your face portrait, you are talking about a star. In one of the examples that I gave when I started teaching you about how to draw face portraits in 2D system was the example which I think looked like this: dx by dt is equal to ax and dy by dt is equal to minus y. And when a was equal to minus 1, it became like this: dx by dt is equal to minus x and dy by dt is equal to minus y. And all the flow lines that were coming to the fixed point 0, 0 were straight lines. That's an example of star node, star fixed point. Now it can be an unstable fixed point or a stable fixed point, it can be both. A degenerate node, on the other hand, is when your eigenvectors, they coincide with each other. This is also, I think, something I covered in the class, but I don't mind repeating it. So let me share my screen and show you an example of both. So let's say, okay, sorry, so let's say this is x and y and we are dealing with a situation where dx by dt is equal to minus x and dy by dt is equal to minus y. In this scenario, your fixed point, which is 0, 0, it's an attractor, so it's a stable fixed point, and we can show it by coloring it. And all the flow lines will go like straight lines. Okay, that one was not a very straight line, but I hope you get the idea. I just used the line tool. Now this is an example of a star node. Okay, so all the lines are going to be straight lines and they're going to come towards fixed point. Fixed point can be 0, 0, it can be anything, doesn't matter. How will you know this? You will know this when you draw. Remember I told you that I shared this with you earlier, that the flow lines are always tangential to the slower eigenvector. So for example, if this is x and this is y, and let's say this is eigenvector 1 and this is eigenvector 2. So let's say eigenvector 1 corresponding lambda is lambda 1 and eigenvector 2 corresponding lambda is lambda 2, and let's say that the magnitude of lambda 1 is less than the magnitude of lambda 2. So the slower eigenvector will be v1 because lambda 1 magnitude is less than lambda 2. Please notice it is the magnitude, not lambda 1. So in this case, all the flow lines approaching the fixed point will approach and be tangential to v1. So whether it's an attractor or a repeller, all the flow lines will be tangential to this particular eigenvector. Now okay, the page on which I am drawing, the curve is coming really nice, but I just looked at the screen, it's all wiggly. So let me redraw this. So let's say this is v1 and this is v2. Okay, this is a new writing software for me, folks. So all the lines, since v1 is the smaller eigenvector, all lines will be tangential to v1. All the flow lines, whether it's an attractor or a repeller, are going to be tangential to the eigenvector v1. This is important. Again, wiggly lines, no idea why. Now what happens when both eigenvectors are equally slow or equally fast, which is lambda 1 is equal to lambda 2. that is when you get a case of star node. Since they are both equally slow or equally fast, the lines that will approach the fixed point will be straight lines. This will be the case. Okay, now let's look at the case of degenerate nodes. Let me change the sheet. Just very good questions, SK. Thanks for being here. I see we are running out of time, so I'll have to ask my team how much more time I can take. And of course, students, I will love to schedule another session, answer some of your questions, maybe go through assignments with you. I will try to share practice questions this weekend itself. So if you have any questions regarding the practice questions, you can ask them next time when we meet. Okay, so degenerate nodes. Degenerate nodes. So remember what I told you. I told you that the flow lines will be tangential to the slower eigenvector. So let's say this is x, this is y, and I have to, let me change the color to make life little. Okay, let's stick with the same color. So we have v1, we have v2, and v1 is a slower eigenvector, so all the flow lines are tangential. Okay. Now what happens when v1 and v2 start coming very close to each other? Now v1 is still the slower one, but v1 and v2 have become very close. The angle between them is reducing. If you look at this angle, and if you look at this angle, it's becoming flat, becoming 180, and this one is becoming 0. What happens then? So the lines still want to be tangential to v1. Yeah, so they still want to come and they want to approach. They don't want to come tangential to v2. They still want to approach and be tangential to v1. They're okay taking the longer path. The flow lines are going to be tangential to v1. Let them come even closer. So now this is v1 and v2 is also very close. So the lines are still going to be tangential to v1. But they are very close. Now what happens when v1 and v2 completely coincide? Similar behavior. The lines are going to try. So this is a case of degenerate node. When the eigenvectors have coincided with each other. When the eigenvectors coincide with each other, but the flow lines still behave as if they are infinitesimally separated from each other, then we are dealing with degenerate nodes. So there are two very different things. Degenerate nodes is that eigenvectors are coinciding. So when you calculate, you will get same eigenvectors for different eigenvalues. And then star node is different eigenvectors, same eigenvalues. I hope that is clear. Okay, let's look at other questions. Ma'am, non-dimensionalizing is the toughest thing in the course. Would be grateful if you could explain. The examples you non-dimensionalize in the class required intuition to decide what to divide with. But you also said that you knew what to divide with because you had already seen what the final model looked like. Please provide a simple way to non-dimensionalize. Okay, so SK, this is a very important question. To non-dimensionalize, some level of intuition is required But what is even more important is to realize that there are, okay, let me make it very easy for you. Unless I specifically tell you that this is what you should get after non-dimensionalizing, remember that there is no correct way of non-dimensional, no single correct way of non-dimensionalizing. As long as you have ensured that there is no parameter, no variable in your entire model that has any dimension, you have successfully non-dimensionalized your system. So for example, in insect outbreak model, you have two options. You can either take n by k as a new variable, or you can take x by a or x by b as a new n by a or n by b as your new variable. Both of them will give you a non-dimensionalized answer. One of those answers will match the answer that I wanted. So if I specifically tell you that, hey, show that this system on non-dimensionalizing looks like this, only in that case is there a right way of non-dimensionalizing. So how do you know how to figure that out? How do you know how to figure that out? That is by just try and error. You try, and if you get the same solution as I want on the first go, good for you. If you don't, try again. Like this time choose some other variable. Now there are some tricks to the trade. The trick to the trade is always try to start with choosing a particular set of variable and numbers, constants, as a new variable, which are already non-dimensionalized. So look at your model carefully and see, is there any scenario where you have constant plus minus variable divided by some constant? And the reason is the constant will have no unit. Constant plus minus can only happen with a no unit situation, non-dimensional situation. So for example, in logistic curve, inside the bracket, we have 1 minus n by k. 1 is a constant, it has no unit, no dimension. It's non-dimensionalized already. Minus n by k. Now since n by k is getting subtracted from 1, then n by k also has to be non-dimensional. So n by k is a good candidate for starting your non-dimensionalizing journey. Maybe take n by k is a constant, n is a variable. So maybe take n by k as x, your new variable, non-dimensional variable. So please write this down, this would be helpful for you. The first step is look for places in your model that are already non-dimensional. And then, and make sure there's only one variable, and as many constants as there are doesn't matter. It can be n by k, it can be n by k1, k2, k4, doesn't matter, as long as they're all constant. And then maybe use that to define your new non-dimensional variable. So logistic equation has a very good example where you have a number plus minus something. The plus minus something will always be non-dimensional already because number is non-dimensional. The other is look for what is e to the power something. If you have e to the power something, then it is given that the power of e should be non-dimensional. So some constant into variable kxt, for example, then k will make the product of xt non-dimensional. You know this. So then you can say kxt, like for example, you have e to the power minus kx. Then kx is non-dimensional for sure. So you can say kx is equal to y. The other is look for what is inside logarithmic. Anything inside logarithm will be non-dimensional. It has to be a number. So these are some tricks. But the underlying philosophy of the trick is look for places in your model that are already non-dimensional and start from there. Ma'am, but then if there is no correct way, good follow-up question. We can simply show LHS is equal to RHS, LHS by RHS is equal to 1 using the first basic equation to non-dimensionalize. Okay, the idea of non-dimensionalizing is not to simplify the model. Let me be very clear here. The idea of non-dimensionalizing is to make things comparable. For example, if I'm looking at the rate at which human population grows and the rate at which mass extinction is happening, if I'm modeling these two things. So right now, we are under 6th mass extinction event, and this is the fastest mass extinction that we have seen, our Earth, our life has ever seen. And I want to model the extinction of species and the growth rate of human civilization. And human civilization is growing very fast, but not as fast as species are going extinct. So species are going extinct every day. Human civilization is not growing every day. So in order to make them comparable, let's say human civilization grows in decades, and there's a way in which I'm defining growth for human civilization, let's say. And extinction is happening every day. So I should be able to compare what's happening on a daily basis with what's happening on a decade basis. To compare them, I need to get rid of time. I need to get rid of the dimension of time, because on time they are ranging from per day basis and per decade basis. So if I have a non-dimensional version of time, tau, then it's easier for me to compare. Because now tau has nothing to do with a dimensional time. It has something to do with something else. So maybe it has something to do with the reproduction rate, the rate at which human beings grow. So by the time 4 generations of human beings grow, 3 generations of species may not be present. That should have been present. So the 3 generations of species might be happening on a weekly basis, monthly basis, doesn't matter, because I have non-dimensionalized the time. So the point of non-dimensionalizing is not to make it simple, but the point of non-dimensionalizing is to make things comparable. And I think I explained this when I talked about insect outbreak model, that insects grow so slowly, the birds grow faster. The insects grow really fast, the birds grow slowly, the birds that are eating them, and the foliage, the trees that the insects eat, the birdworm eats, spruce birdworms, they take much longer to grow those trees and foliage. So how do we compare all these things? The insects are growing on a daily basis, the birds take 1 year to grow, the trees take decades to grow. How do we put all these varying time scales together? We put them together by non-dimensionalizing the system. When you have a non-dimensionalizing system, there is a non-dimensional time entity, there are non-dimensional number entities that are working. Since they are non-dimensional, they are all comparable. So the idea is not to simplify it. Now when you are saying there is no correct way, can we simply show LHS by RHS is equal to 1? That's always true. Any model that says dx by dt is equal to something, just divide LHS by RHS, and that will be equal to 1. But that's not what you want to show. When you're non-dimensionalizing, remember everybody, the idea is that every variable, every constant should have no dimension. Whatever is left should be non-dimensional. And another important thing is, the way you can go wrong in non-dimensionalizing is that if you have already defined a variable, don't redefine it. If I've already defined kx is equal to y, don't say x by c is also equal to z, because a non-dimensional version of x already exists, which is kx is equal to y. Once you have taken care of x, please don't redefine some other variation of x as a new variable. Don't do that. I hope you are clear about how to non-dimensionalize, not how to non-dimensionalize, but what non-dimensionalization is and how to go about it. Yeah? I'll take a short water break and then I'll get back to your rest of the questions. I don't know how many students still have time to attend to and look at some examples that I wanted to solve to give you an idea of the kind of questions. Okay, SK does want to solve some questions. Let me take a short water break and then we'll get there. Yeah? Okay, let's solve a simple question, and as promised earlier, I want to take a simple question that has a simple trigonometric function. It doesn't matter whether it is trigonometric or logarithmic, same principles apply. And the question is, draw the phase portrait, figure out the stability of fixed points, and it's a tricky question. Okay, Satya, I'll look at your question too, but let's look at this question first, okay? Satya has 3 questions. Cos x, 1 plus half cos x, ex plus cos x. Okay, Satya, I will take a version of your third question and then we'll solve it, alright? I'll take a version of your question, Satya, and I'm going to make it even more tricky. So, dx by dt and, okay, hold on. Everybody I know is getting sick here. Take care of your health, folks. I don't know where you are if there's an issue with viral fevers, but please stay healthy, everybody. So the question that you gave, Satya, was you gave 3 questions. The last one is ex plus cos x. Okay, students, should I stick with this one or should I make it more tricky? I just finished midterm exams of my students here at IIT Roorkee, and the question I asked them is more tricky than this one. So, oh, please share the screen. Okay. Tricky? Alright, let's make it slightly more tricky. Okay, so here is the question that Satya shared. So let's make it more tricky. Let's add an x here. Something similar I asked the students in the midterm exam here at IIT Roorkee, and it stumped them. So this is a tricky question. Okay, so how do we find out the fixed points? So remember I told you to find the fixed points, we want to find out when dx by dt is equal to 0. And remember here the idea is not to just find the fixed points, but we are going to draw the phase portrait. This is the whole idea. Excuse me. Okay, so to find the fixed points, we need to find out all the points where my dx by dt will become equal to 0. So this should remind you of our very basic high school and 11th, 12th mathematics, where you have a function and you have to find out for what value of x is this function equal to 0. So right, we have x, ex plus cos x equal to 0. You remember? Factorize, figure out. So when we factorize this, yeah, it's very simple. It's already factorized. It's very simple that one of the situations where dx by dt will be equal to 0 is when x is equal to 0. The other situation where dx by dt is equal to 0, if x is not equal to 0, is when e to the power x will be equal to minus cos x. Yeah? In these two scenarios, we know that we'll know our fixed points. The first fixed point is pretty obvious, the second fixed point not so much. So let's find out the second fixed point. Ex is equal to minus cos x, right? So for Ex is equal to minus cos x means Ex plus cos x is equal to 0. Yeah? So this is function 1. Again, think about it this way. And if we can write it in this way, function 1 minus function 2, then we can use the principle we talked about earlier in the class, right? So if we write it this way, like Ex minus cos x is equal to, well, we don't have to write equal to 0 every time, but okay. Yeah. Now what I have done is I have written it as function 1 minus function 2, where function 1 is Ex and function 2 is minus cos x. Now if I'm able to plot these two functions, then I'll be able to find out when their summation is equal to 0. So let's start. This is my face portrait. X equal to 0 is already a fixed point, so let's draw a circle around it to show that we know that x equal to 0 is already a fixed point. Let's not forget it. And even though you'll be like, yeah, by adding in x to Satya's question, really how tricky did it get? You will figure that out when we talk about the quality of the fixed points. I'll go very slowly, so please bear with me. Okay. So we have function 1, function 2. So let's plot function 1 first. Function 1 is e to the power x. How does e to the power x look like? When x is equal to 0, it's equal to 1. Let's say 1 is here somewhere. And as x increases to plus infinity, it rapidly increases, literally undergoes exponential growth. And as x reduces to minus infinity, it undergoes a decay. Yeah, so this is my function 1. Now let's draw function 2. What is function 2? It is minus of cos x. Please do not forget this precious minus. It is minus of cos x. What does that tell me? It tells me it's going to be the opposite of what cos x is going to look like. When x is equal to 0, cos x is equal to 1. Minus cos x is equal to minus 1. So we are starting here. Oh, sorry. 1 was supposed to be here, right? So I need to go higher. Let me erase this. And then let's continue. And I can't go further on the left because the page has ended, but you see, we'll have infinite intersection points on the left side. Okay. Now, wherever the line, not line, sorry, there's no line, wherever F1 and F2, wherever these two functions intersect, their values are equal, which means that's a fixed point. So we have one fixed point here, we have one fixed point here, somewhere here, we have one fixed point here, and we have infinite fixed points to the left. Yeah? So you see, we have so many fixed points. So now we have figured out fixed points. I don't need you to go all the way to minus pi, minus 10 pi, minus 20 pi, or even minus infinity. Please no. Just few fixed points are enough for me to understand that you know. Now comes the tricky part. Figure out the stability of these fixed points. Ooh. So remember, to figure out the stability of these fixed points, I told you that you have to look at the signs of your functions. So I want to redraw this more neatly so that because it's going to get very messy very fast. So we have one fixed point. Do not forget this fixed point x equal to 0, folks. This is a tricky fixed point, and you'll figure out very soon why. So our equation looks like this. dx by dt is equal to x into ex plus cos x, which we chose to rewrite as x into ex minus cos x. Clear? Why did we do this? Because we wanted to write this as function 1 and this as function 2 to make our life easy and figure out the fixed points. Because if I had not written it like this, I wouldn't know all these fixed points, right? Okay, so now let's figure out the stability. So let's start, you can start anywhere, from left side or from right side. Let's start from the right side because there's so many fixed points on the left side. Okay, so let's start with x equal to 0. To the right of x equal to 0, I'm going to choose another color. To the right of x equal to 0, x, this part, is positive. X is positive. Function 1 minus function 2. What about function 1 minus function 2? Is it positive or is it negative? Think about it. Function 1 is above function 2. When function 1 is above function 2, their difference will be positive. f1 minus f2 will be positive. This is f2. Right? So f1 minus f2 is positive, which means this is also positive. So positive into positive is equal to positive. So which means dx by dt is positive. Let me write this more nicely here. dx by dt is positive is positive to the right of x equal to 0, which means the flow is towards right side. When dx by dt is positive, which means x is increasing, the flow will be towards plus infinity. Now let's look at what happens to the left of x equal to 0. Immediate left, we don't want to go beyond the next fixed point. So to the immediate left of the fixed point, x equal to 0, what happens? Let me change the color here. First of all, x becomes negative. This is where I said this becomes little tricky. X becomes negative. This is very important to understand. When x becomes negative, it is a very important thing to account for when we are looking at the sign of dx by dt, because x equal to 0, to the left of it, x is negative. Now what happens to ex minus cos x, function 1 minus function 2? Function 1 is still above function 2. Function 2 is here, function 1 is here, right? So function 1 minus function 2 is still going to be positive, which means ex minus cos x is going to be positive, which means this function is still going to be positive. So now we have a scene where minus into plus is equal to minus. So here dx by dt is a situation where minus into plus is happening. This is less than 0. Less than 0. So here the flow is going to be towards left side. Some of you already know this means x equal to 0 is an unstable fixed point. Let's look at the second fixed point, okay? To the right side of the second fixed point, the flow is towards left side, dx by dt is negative. To the left side of the second fixed point, so we don't need to look what happens when we go to the right side, we already know what's going to happen. Let's look at what happens when we go to the left side of the second fixed point. What happens when we go to the left side? Let me change the color again. X is still negative. We are still in the negative zone. Okay, there is some movement of the paper. Let me erase this and start again. Yeah, x is still negative. Let's look at function 1 minus function 2, or ex minus minus cos x, or ex plus cos x. What's happening there? Ex function 1 is below function 2. This is function 1 and this is function 2. When function 1 is below function 2, f1 minus f2 is going to be negative. So now we are dealing with a situation when we have negative multiplied by negative. What happens when minus into minus happens? Dx by dt becomes positive. Minus into minus is plus. So the flow between these two fixed points is to the right. So what kind of stability does the second fixed point from the right has? It's a stable fixed point. Similarly, you can find out. So how do I show stable fixed point? Make a circle, color it nicely. Similarly, you can find out the stability of other fixed points. Okay, so this was one question we solved. Let's go back to your comments and your questions. Okay, SK, alright. Tricky here but simple in the exam. Okay, SK, I agree with you. I think I'll definitely do this. I'll share the practice questions today itself. Remember, they're not sample questions, they're practice questions, but if you practice them, you should be well prepared for the exam. I'll do that. Oh, Satya, thank you so much for offering me to take warm water. I just recovered from a viral. I hope I don't get it again, but thank you. Yes, I will give sample questions, Vinita, and as SK requested, I will at least share with my NPTEL team today, my learning center today, and then I think they're very prompt and professional, so they should be able to upload right away. I mean, I don't know how long it will take, I cannot make promises, but from my end, I will share today. We have already gone 38 minutes longer than planned. I hope this was helpful for you. Once I have shared practice questions, I will insist that we have another meeting, preferably same time next week, a live session where you can ask questions from the practice questions. I'll ask you to practice questions that are very basic, that deal with basic concepts, and once you are able to solve them, I'm quite confident you'll be able to do it in the exams. What does pen paper exam look like? Request to share answer sheet format too. Will the calculator will be on screen only? Calculators are typically not required for this exam because there will not be any major calculations. As you can see, I solved a question in front of you, almost completely solved it, but I didn't need any calculator. So don't worry about needing a calculator. With this question paper, I don't solve, there might be some questions though, which might require some multiplication and division. Yeah, I think you'll be allowed. I need to check that with the NPTEL people. I'm not quite sure. You will definitely not get an on-screen calculator. I do not know if they'll provide you a calculator or if you're supposed to get one yours. I do not know. I'll have to ask NPTEL. If you have a local NPTEL office, you can ask them for confirmation. but I'll write this question down regarding calculator so that next time when we meet I'm able to answer your question. What does pen paper exam look like? You know how you have exams in your universities? Okay, SK, I understand. I'll look into it. If I have the option, I'll definitely encourage and ask NPTEL to let you bring your calculator. But again, no promises. Next week, I will be able to give you a definite answer. Meanwhile, you can also reach to your NPTEL office. Okay, how does pen paper exam look like? You know, you have exams in your university, in your institutes, where they literally give you answer sheets and say, hey, these are your answer sheets. And here is a question paper, read the questions carefully, write an answer. That's how it will be. You will literally solve the questions on a piece of paper, on an answer sheet, in an answer sheet. You have to write your name, enrollment number very carefully, and then they will be scanned and sent to me, and then here I will grade them, and then the marks will be sent back to you. Yeah. I will definitely keep that calculator request in mind. I'll talk to my learning center right away about this. Okay, students, I would like to wrap up now. It was a long session, went 40 minutes longer than I expected it to be. Once you go through the practice questions, please come with questions regarding the practice questions also next week. Yeah? Satya has one last question. I hope it's the last question for today. Will you arrange model exam for this paper before the exam? I don't know if NPTEL has a policy for arranging a model exam, but that's something to ask NPTEL about it. Let me write that down too. Okay, so we'll see. I'll answer all your questions that I don't know answers to regarding calculator, regarding model exam. Okay? Yeah, I think this is a good time to wrap up for now, and then we'll meet in the next week. Hopefully next week there'll be another live session. Thank you.